So continuing on with our discussion of linear distortion, let's take a look at a MATLAB example where we can see how this happens using a bit more detail than the crude drawings I had in the previous video. So let's imagine a transfer function that looks like this. It has a non-ideal amplitude response, but it has an ideal phase response. And if you want to remember, right, the ideal transfer function would look like this for the amplitude response and the phase response. So the ideal amplitude response would be such that there is a constant, right? We have a constant k of equal to 1 response across the channel. That's what would be ideal. However, what we're seeing is, right, depending on the frequency, we're having slightly different amplitude responses. It varies from 2 down to 1 at the top of our band. So if we were to pass a signal through our channel, which has this non-ideal amplitude response, but an ideal phase response, this is the type of dispersion you would see. So we're trying to send this triangle through. We send it through a system that has transfer function that looks like this, HF, and now we have a delay of 1.5 milliseconds, which is fine. Everything has the same delay. However, due to this kind of arcing shape across the transfer function, we can clearly see that although this visually looks like a triangle, it has clearly dispersed beyond this 1 millisecond, right? Our initial pulse was just 1 millisecond long. However, this one has spread beyond this. It's spread a total of about 2.25 milliseconds below and 0.25 above for a total of about 0.5 milliseconds. Now, if we were to increase the non-ideal amplitude response even further, so we can see that now this is starting to look like a very, very big arc, we can see that this pulse in time is becoming more and more spread out. And it's also being changed in the magnitude at certain places. And so this is an example of linear distortion with a triangle pulse.